Hey, there we go. Linux has not defeated me yet. Hello, friends. So this is a talk about how to find boundaries in software. It's kind of a high-level, theory-heavy affair, which is exactly what you want after lunch when they've stopped serving coffee, so I apologize. I'm Bob. You can find me on Twitter. I'm currently the engineering coach at Kazoo, where I used to be a chief architect. You can find the slides up on GitHub, including most of the words I'm going to say, because I like to write things out in long form. This is actually the last talk I'm going to do as a Kazoo employee, because I'm moving on to a new gig for a company called Carbon Re, working to decarbonize heavy industry. So I'm going to be hanging around in the bar for most of the conference. You can come and talk to me about climate change. Statistically, probably 80 to 90% of you are either terrified or worried about climate change, and maybe 1 in 5 of you will have had a conversation about it in the last year. And we need to talk about it. It's really important. So come and have a chat. I'm also on a personal mission. I want to get as many smart people as possible working in climate tech. So if you want to work in climate tech and you don't know where to start, come and chat. And lastly, if you're sat in the crowd thinking, I know all of this, I could give a talk about that, you're probably right. And again, if you don't know where to get started, come and have a chat so you can have some new faces up on stage next time. So why this talk? So partly I'm doing this talk because I feel like as a community, we don't spend nearly enough time talking about fundamentals. So people spend a lot of time talking about new libraries, new techniques, new AWS services, but we rarely take the time to step back and reflect on kind of fundamental principles. And I've been working at Kazoo for a few years. For those of you who don't know, Kazoo is an online car dealership. So we buy cars from various places. We make them look pretty by fixing the dents and painting them and that kind of thing. And then we sell them online and we deliver them to your house. And for a while, Kazoo was almost certainly the fastest growing business in the world. So we built the first version of the application, that's delivery, e-commerce, payments, consumer finance, refurbishing, everything in about 90 days from start to finish. We did 100 million quid in revenue in our first year, and we launched on the New York Stock Exchange for $8 billion after 18 months. And so people would say to me, you've built this thing in about 5 minutes flat. What kind of scaling challenges did you have? Do you have like technical debt? Like, what was that like? And I have to explain that, we'd used Dynamo and Lambda and S3 and all these very boring, stable technologies. So actually scaling wasn't a problem. The thing that's hard, I would say, is how do you take this huge problem, all of these massive, massive problems, and divide them up in a way that makes sense? So this is the stuff, boundaries and how to design software systems that we'll grill you about if you come to Kazoo to interview as a principal engineer or an architect. And very often when I interview people for those roles, they don't really have any formal model for talking about them, or they misapply a whole bunch of terms. So the boundaries of things are important because if you get them wrong, they will screw you up in painful and unexpected ways. So I'm going to talk about 3 lenses that I use when I'm thinking about the boundaries of things. It's going to be a kind of a whistle-stop tour. We don't have time to talk about all of domain-driven design today, unfortunately. There'll be a bunch of links throughout, and you can catch me at the conference and have a chat if you're interested in something. So the first and most fundamental lens we're going to talk about is coupling. What is coupling? Usually, when we talk about coupling in software engineering, we mean that when one part of a system, some other part has to change in response. Is coupling bad? Give me a show of hands. Does anyone think coupling is bad? Does anyone think coupling is good? Does anyone think it's a trick question and you're not going to answer me whatever I say? Yeah. Those are the future architects right there. So coupling is necessary, right? We can't completely eliminate coupling from code because coupling is a consequence of the fact that one thing is talking to another. You can invent fancy systems for doing all the wiring up at runtime. Really, that just moves the coupling to somewhere else, usually to your magical system, and that's probably not a wise trade-off. But people often have a very simplistic view of coupling, right? So in particular, a lot of software engineers will tell me coupling is bad, but reuse is good. So one of the classic dicta of software engineering is DRY, right? Don't repeat yourself. But if you follow this rule, things end up coupled. Why? Well, because if you put every piece of knowledge in exactly one place, then everything that needs to use that piece of knowledge ends up coupled to that one place, right? It's obvious. So let's imagine you work for a company who builds, web applications, and your company builds a bunch of APIs and backends for front end and micro front ends and all that jazz. And some wise ass says, the API type definitions, like the schemas, are shared between the server and the client. That's a violation of DRY. We should extract an NPM package so they're all in the one place. This is a terrible idea, okay? This is a horrible, no good, very bad idea that will not die. It's a terrible idea because now every change to your API requires a change to the package and then to the clients. So what you've done is you've taken things that were coupled very loosely by some shared schema and you've coupled them at build time, which is a much stronger form of coupling. And people do this all the time because of this kind of broken idea of DRY that they are misapplying. So is reuse bad? No, of course not, right? But we have to be mindful, right? DRY is a really useful heuristic in the right context, but reuse means coupling. So the first heuristic we should use is this one, right? Things that change together, ship together. What does it mean? Well, it means if you've got two functions, two classes, two APIs, whatever, and when you change one of them, you also have to change the other, then you should deploy those things together, okay? Don't pretend that they're independent, right? Often I see teams and they've got an API and a single-page application, and the only client of their API is the single-page application, but they insist on deploying them separately because they're decoupled. They're not independent things, so deploy them together. If you want to ship two things independently, you have to uncouple them, even if that means copying code or copying data, okay? Reuse is not your friend here. So things that change together go in the same module, in the same class, in the same package, in the same system. Generically, we say they form a deployment boundary. And a deployment boundary is a line we can draw where everything inside the line ships at the same time, and everything outside of the line does not. So I hope everyone sees, ideally, we want deployment boundaries to be small. So a smaller deployment boundary means less stuff to test. It means you're less likely to break things when you deploy. And if I've got a system and I divide it into 3 separate deployment boundaries, I can have 3 teams all working on their thing in parallel and shipping whenever they like. So these days, of course, we do this through microservices. If anyone manages to scan one of these QR codes, by the way, let me know, because I've got no idea if this is a great idea or a waste of time, and it'd be good to have some feedback. So the original microservices paper was written by some guys at ThoughtWorks, and they've been experimenting with dividing up projects into small pieces so they could deliver them in parallel. And this is what Kazoo did, right? So right from the beginning, in order to build things very quickly, we spun up multiple teams, and those teams tackled pieces of the larger problem. So each of our microservices at Kazoo is a CloudFormation stack. It goes in its own GitHub repository because we deploy it all together and it's all versioned at the same time. And we use the serverless framework to define the resources that we use. Note that a single Lambda function is usually not a microservice, okay? A service can have many components. And in particular, we might have a single database that is accessed by multiple functions. And such functions are coupled. Okay, so if we've got this library borrowing service where you can check a book out and check a book in and reserve a book, they all need to use this same database, and therefore they are coupled. Because if we need to change the way that we check books in and out, that change can ripple to the other functions. So they form a single deployment boundary. They have to ship together. So at this point, it's 2022, and everybody knows that microservices don't share databases. But this is why. If 2 components share a database, then they are coupled by that database schema. You can't change it independently. They form a single deployment boundary. We might also have a domain model that's used by multiple functions, okay? So imagine we're building our library application. You might need an application for checking books in and reserving them. It's likely that we want some shared code base across all of those functions. Each of the functions uses our shared code base as a library, and that again means that they're coupled just as they were by the database. This is why you should avoid sharing libraries between microservices as much as possible, right? Don't repeat yourself turns out to be a terrible heuristic when you're doing microservice architectures, because reuse is coupling, and the whole point of doing microservices in the first place was to decouple these isolated pieces. So there's another kind of coupling that's present in our systems, and that is temporal coupling. So if one component is temporally coupled to another, it's unable to return a result independently, right? So in this situation, we've got our library web app, and it talks to the back end for front end. You want to check out a book, so the checkout API has to call the book API to get some details, and then the back end for front end is going to call the user service to say this user's got the book. This kind of RPC-oriented integration is really common in the microservice community, and it is also terrible and bad and horrible and no good, and you shouldn't do it, because this checkout service can't do its job independently if one of the other services is broken. So in other words, the checkout service is coupled to these other services in time. A request that comes in at the bottom can't be completed until all the others have been completed. If one of them breaks, so does your initiating request. So the solution to that is we want to avoid synchronous calls between systems as much as possible. We want to do the smallest amount of work we can in the checkout service, and then the rest of the work can happen later. So in our case, that means we want to record that a user has checked out a book, and then raise an event, book checked out. And then the book service can receive that event and update its local data store. This way, the original request is able to complete, even if there's a problem in the book service, right? So this is a temporal boundary. We've drawn a line where some things have to happen together, and other things can happen later. They can be deferred. So Kazoo do this a lot, right? We hardly have any service-to-service API calls. Instead, everything is driven through events that occur at the end of a process handover. For example, when you buy a car, we raise an event called order placed, and we use that to trigger payments and to take the car off the website and to schedule your delivery. The only thing that needs to happen synchronously is our storing your order details into our local database. But event-driven architecture is tricky for a bunch of reasons. And primarily it's tricky because you have to give up on the notion of consistency between your components. So our first lens is coupling. We need to understand how changes ripple through our system and how components are temporally coupled. We want to draw small deployment boundaries and small temporal boundaries, use microservices to ship small systems, and use events to communicate between them. Our second lens is consistency. So consistency is the property that two requests through a system will see a view of state that makes sense, right? So in our library system, either you've got the book checked out or you haven't. It is not Schrodinger's bookshelf. And consistency is important whenever you want to make a decision. For example, when you return a book to the library, if it's late, we want to charge a penalty fee. It would suck if I returned the book and you ended up paying the charge, right? That wouldn't be fair. That could happen if the data are inconsistent somehow. So without consistency, it's hard to make decisions because the facts you're basing decisions on might be wrong. There's more than one kind of consistency, and you need to be aware of which kind you have and which kind you need. So a system is strongly consistent if every process accessing that state will see all of the updates to it in the same order, okay? So if you've got the getBook function and the checkoutBook function, they all see all of the updates in the same order, and so they can agree on who's got the book checked out. In a strongly consistent system, there is only a single shared view of state. If a system is eventually consistent, then processes using the system will eventually agree on the state. But in the meantime, you've got this kind of intermediate state. So here we've got two processes. They both see some subset of those updates. So no one really knows who's got the book checked out. So a good example of an eventually consistent system is DNS, right? If you add a new DNS record, it takes time to propagate across the internet. Some parts of the internet will see it after 5 minutes, some maybe after 24 hours. But so long as you don't keep changing the settings, eventually every part of the internet will agree on what the value is for that DNS entry. So in our library system, that might mean that when we check out a book, it doesn't immediately show on the search page that it's not available. And this is the case for Kazoo. So when you buy a car, you raise order placed, and it's the order placed event that triggers us to take it off the website for sale. In the early days, that sometimes meant that went wrong, and then more than one customer would buy the same car, which was a little bit embarrassing, and I have to explain to the CTO about this event-driven architecture thing. Big oops. So consistency is the first casualty of temporal decoupling, right? Temporal decoupling, we want to keep it as small as possible, but as soon as we temporally decouple things, we have to give up on strong consistency, and that makes things hard. It's hard because if two separate requests commutate the same piece of state, you can end up in undesirable states. What is an undesirable state? Well, imagine this is your granny, and she's using the website that her very clever grandchild has built for her so that she can reserve books over the internet and collect them from her local branch. She is extremely proud of you. Your granny's using the library website to browse books by Maeve Binchy. Right? She's looking at the web page for book number 12345, and she clicks reserve on that book. But unbeknownst to your granny, the librarian is in the background updating the catalogue, removing old books and creating new ones. And they've updated that book 12345 with the result that your granny has actually reserved Dirty Lust Volume 4, guaranteeing an awkward conversation for everybody when she arrives at the branch to pick it up, okay? This is an undesirable state. Your gran did not mean to check out Dirty Lust Volume 4. She wanted the Maeve Binchy book. But the consistency boundaries did not align with the user intent, so we can end up recording things that our user never intended. Now, there's two ways to handle this case, right? Either you stop it from happening at all, or you build a system that expects this kind of thing to happen and handles it gracefully. So the classic way to handle concurrency issues in a data-centric system is to use locking. And the core idea of locking is that only one client can access a piece of data at once. In relational databases, we handle this by actually locking rows of data or sometimes entire tables. But this reduces the potential throughput of your system, right? The whole point is only one client can access the data, and that means you can only handle that one request at a time. So here's your granny, and she's locked books number 1, and she's locked the checkout table. So your granny could lock that book she was looking at, and then the librarian, when the librarian comes to change that book, they're going to get their request rejected. If you've got lots of grannies, though, not you personally, but if we collectively have lots of grannies, all looking at bits of the catalogue, no one's going to be able to change anything, and that's going to get very frustrating. And in particular, you can get this situation, where your granny has locked the book and wants to lock the checkout table, but the librarian has locked the checkout table and wants to lock the book, and so nobody can get the complete subset of objects they're looking for. This is a deadlock, and essentially the database will just hang and wait for somebody to get bored and go elsewhere, right? So I've spoken to teams before who are deeply freaked out by concurrency, and they insist that they need to have like serialized access to all their tables in order to avoid race conditions. And they're generally wrong about this, but they haven't thought about the consistency boundaries that would make the most sense for their problem. So in domain-driven design, we use the aggregate pattern, where the idea is that we match our consistency boundaries with the domain model. And an aggregate is a collection of related objects. So one of the classic examples, maybe not a good example, but a classic example is a shopping cart. So in a shopping cart, I've got the cart itself, which has got some identifier, a cart ID. It's related to a customer session and so on. And then I've got the cart items, which relate to a product. They've got a price, a quantity, and so on. The cart and its items together make up an aggregate. Okay? It is a cluster of objects that change together. And we use our database to enforce consistency at the aggregate level. So if I've got two shopping carts, they can both change independently, but only one person can change a single cart at a time. So aggregates are a consistency boundary. When we want to make a change, let's say I want to add an item, we do that by loading the whole cart out of the database, making the change in our domain model, and then persisting the whole thing again. We never interact with the items one at a time. We only work through this public interface, the cart. Right? The cart represents the scope of our persistent state. Typically, we use a repository pattern here, right? Repositories load aggregates from data stores. That's what they're for. There is no repository for loading cart item, because there is no way to get hold of a cart item except by loading the whole cart and calling a method on that object. Why? Well, because the cart is our consistency boundary. So the only way to make changes to the items is to fetch the cart. That means you never need to lock the cart items table at all, right? In our model, we never need to lock the checkout table at all because we're locking the book, and the book is our consistency boundary. This means we can't end up in a situation where the librarian has locked one part and we've locked another, because we only need to lock a single object at a time, right? The trade-off is that we then need to manage the consistency ourselves inside our domain model. So in serverless, we tend not to use relational databases because they're a pig in nuisance, and you need connection pools and usernames and schema migrations and all that boring stuff we want to leave to Amazon, right? Instead, the database of choice for serverless applications is DynamoDB. Objects in DynamoDB have got two keys, right? They've got the partition key and they've got the sort key. And every operation in the Dynamo API, except for scans, requires a partition key. Why? Well, it's because the partition is the unit of consistency, right? When you make a request, Dynamo, it routes it to a specific set of physical machines based on that partition key. So if you want to make a change, you have to make a change to that single partition. So in serverless, one aggregate maps to one partition key. So the easiest way to implement a lock in DynamoDB is to use version numbers, right? So we could create a new book object, and then when we create the book, it's at version 0. When your granny reads the book out of the data store, we fetch the version number, so she's got version 0 of the book. When the librarian updates the book, we increment that version to version 1. Now when grandma tries to reserve the book, we notice there is a version mismatch, and we can reject her request. Usually when this happens, we just have to retry the operation, run our domain logic again and see what happens, and everything will be fine. In this specific and embarrassing case, we will have to reload the web page and show Granny what she's about to do. But then she gets to make a choice, right? She can go and look for another book, or she can stick with Dirty Lust because God knows your granddad could use the pointers. So DynamoDB uses condition expressions to provide optimistic concurrency. The link here is to Alex Debris' site. Caveat, he uses the word aggregate on this page to mean things like a sum or an average, like an aggregate over data, not using it in the DDD sense, but it's a really good overview of how to use conditional expressions in your designs. So we want to create a new cart. We can use a condition expression to say, insert this cart only if the cart does not exist. Okay, we're going to insert a cart at version 0, but will fail if that partition key, that aggregate, is already in the table. When we want to update our cart, we use an update expression. So this expression, this unwieldy blob of JSON, will add 1 to our version. That's here in the update expression. But it will fail if the version does not equal the value we were expecting, right, this previous value. So there's some sample code for this in the GitHub repository. You can take a look. It's for example purposes only. Please don't put it into production and then blame me. But it does show you the basic concepts and how these things fit together. So the aggregate pattern was first described as a solution to relational database performance problems, right? We have this trade-off where we can lock more so that only one person can lock the library at a time, or we can lock less so that we have a faster website, but your granny can accidentally check out porn. In the aggregate pattern, we explicitly define consistency boundaries at the domain model level. So instead of relying on our database to figure out what to lock, we build our own locks, right? And this makes it easier for us to reason about consistency. So within one aggregate, right, within our book aggregate, we have strong consistency. Every access to the book will see all of the checkouts, it will see all of the updates to that book in the same order. But between aggregates, we rely on eventual consistency. This is because, again, we only need consistency when we're making decisions. And in this context, a decision is some policy that we apply when we change state in our system. So coming back to Kazoo, it's important that when you pay for a shopping cart, you pay the right amount for the goods you've got, right? Because otherwise, maybe there'd be a bug where you can add a car and add a pair of fuzzy dice and then somehow only pay for the fuzzy dice, right? That, again, is an undesirable state. The biggest problem people have when designing aggregates is they make them too large, right? Because people think they need more consistency than they actually do. So in our library model, customers need to be able to check books in and out. They should be able to reserve books over the internet. And they should receive fines if they return a book late. So what are the aggregates?
So our first thought might be that the aggregate is the book. Books are clearly important objects in the context of our library system, and only one user can check out a book at a time. So isn't that a good consistency boundary? But remember that when I want to mutate the state of an aggregate, I'm going to load the whole thing into memory. Do I need the complete history of a book in order to make borrowing decisions? What are the operations exposed by a book? I can check a book out, I can check a book in. If I apply a fine, do I apply a fine to the book? That doesn't seem right. Fines are applied to a single customer, not to the book as a whole. If I want to check out a book at version 3, but somebody has just paid a fine on version 3, should my request fail? Well, that doesn't seem right either. The consistency boundary is too large. Pragmatically, it makes more sense to choose the loan as the aggregate. What operations does a loan have? Well, I can start a loan, I can return a loaned item, I can report that my dog has eaten the book, and that's it. So the loan contains all the information I need in order to make a decision. Was this book returned on time? So we've made our consistency boundary really small. We require that each individual loan is internally consistent. So we can't have two updates to the same loan at once, but we don't require a single consistent view of the book. In fact, the book doesn't exist in our borrowing model. That seems like a problem, because humans think in terms of books. To solve this, we use view models. So the aggregate pattern is only applicable when we're talking about code that makes decisions. We use repositories and aggregates in code that is going to change state. For code that reads state, we can use a different set of patterns. This is the biggest mistake I see people make with repositories and aggregates, is they think they need to use them across their whole codebase, but they don't. We only need to use these patterns when we're intending to mutate state. We can think about our system as having two sides. So there's the write side, state, and then there's the read side, where we only care about getting data in the quickest way that we can. These two sides don't have to be completely consistent. So long as each loan is consistent, it's okay for our book view to be a few milliseconds behind, because if somebody tries to check out a book, they're going to have to go through this strongly consistent write side. The simplest way to build a system like this, a CQRS system in serverless, is to use change streams. So in this diagram, we've got two Dynamo tables, and you can do this with one table. It's just easier for me to show you with two. The loan aggregate lives up in the table at the top, and whenever we insert a record or modify a record, that results in an event on the change stream. We handle that event with a Lambda function that publishes it over EventBridge. Our subscriber Lambda, down at the bottom, receives that event and updates the search database. So this is how we handle consistency issues between boundaries. We identify the boundary where things need to be strongly consistent, we model those boundaries using the aggregate pattern, and then we use techniques like CQRS to give us eventual consistency between those boundaries. How do we know what needs to be consistent? How do we find that loan aggregate? I think it comes down to cohesion. Cohesion means stickiness. It means that things clump together. So cohesion in the context of software engineering is the degree to which the parts of a thing work together. So the parts of a watch are highly cohesive. They all work together smoothly, and if you remove one part, the whole thing stops. That might seem familiar, right? Cohesion is related to coupling. So what's the difference? Well, the difference is that cohesion is intradependence. It's the connections between parts of the same module. If things are coherent, then they belong together. It's natural for us to put things together that are coherent. Being laser focused on cohesion actually reduces coupling. So in our borrowing context, we need to understand loans and payment fees. But over in our catalog context, we've got catalog items and versions and the physical locations of books. These things don't have any overlap, right? Both of these contexts are highly cohesive, and as a result, there is very little coupling between them. So everyone knows that it's bad to have a utils package, right? It's like a classic anti-pattern. But why is it an anti-pattern? Well, it's because utils packages lack cohesion, okay? It's just stuff that we couldn't find a better place for. So utils packages tend to become these giant balls of string that are all tangled up and they get coupled to everything else. So we talked about this back at the beginning. If you've got a borrowing microservice and a catalog microservice, and they both use some shared utils package, then any change to that utils package can ripple out to affect both of these systems. So we've introduced coupling because both things have a shared dependency on this low cohesion library. By contrast, a well-designed package has high cohesion. Inside a package, all the components should be closely related, right? They should be talking to each other. The loan and the penalty fee do go hand in hand. In a well-designed package, we've got a small number of public types, and then a much larger number of private types and functions that abstract over that complexity. This gives us a low surface area. So in our borrowing context, we've only got these two things, loan and penalty fee, and all the internal details are hidden away. By contrast, in a utils package, everything is public by definition. Finding cohesive boundaries is hard. So this is the hardest thing to get right because, like aggregates, the boundaries are often unintuitive at first. This is the thing I was talking about at the beginning, okay? The thing that Kazoo struggled with and still struggle with today. It's really complicated, but I'm going to show you the heuristic I used when we were breaking apart Kazoo, which I think has mostly worked well. So bounded contexts are a way for us to describe subsets of our solution. The overall problem we have is manage a library. But that turns out to be a really big and unwieldy problem. So what we need to do is to break it down into smaller, more manageable chunks. Again, our natural inclination is to look for nouns that we're familiar with. So in our library service, the intuitive solution is to build a book service that does, everything. But if we want to avoid building a giant ball of mud, we need to think in terms of the use cases of our system. We have to look for verbs instead of nouns. So if we look at our use cases, we've really got four major ones, right? Customers borrow items, customers pay fines, librarians maintain catalog items, and both types of user need to be able to query the catalog to see what we've got. Now, each of these is a separate process. Each of these has its own requirements for the model. They're all about books, sort of, but those books don't have much overlap, okay? They're different kinds of thing. So in the borrowing context, we have a lending aggregate with a checkout date and a due date for return. We have a reservation aggregate with an expiry date and a collection date. Now these aggregates aren't strongly consistent, but they are cohesive because they both affect the availability of a book. A reservation will eventually turn into a loan, we hope. When your gran returns Dirty Lust 3 weeks late, she has to pay a penalty fee. Again, this is a separate aggregate. It's not consistent with the other two, but it's part of the same solution space. Over in the catalog context, we have much richer information about a book. So we need to know the title, the classification, the author, and so on. And we need to know which branch has got the physical item. In the search context, we take data from both the borrowing context and the catalog context to build a searchable index for our customers and librarians. In this context, we don't care which user has got the book or if it was returned on time. We only care whether the book is currently available or not. Over in the catalog context, we need to use a classification number that tells us what the book is about. Right? It's a book about gardening, it's a book about roses, it's a book about planting European roses in Asia, whatever it might be. But here in the search context, we can translate that precise classification number to a set of searchable tags. So we take the concepts from one context and we map them to concepts that make more sense locally. And we can construct a map of these concepts like this. So this is called a context map, and it describes how the parts of our system interrelate at a conceptual level. So we draw out the relationships between contexts. So both the borrowing and the search context are downstream of the catalog context because they receive data from it. The payments context depends on Stripe, so you can, pay for stuff. And it's got some code called an ACL, an anti-corruption layer, that converts between Stripe's API model and our internal domain model. So maybe inside our payments context, a payment has got a date and an authorization code and an amount, and that's all we need. But over in Stripe's model, they've obviously got a much richer, more complex model for what a payment looks like. We don't want to be bothered by those details, so we build a piece of code, like an adapter essentially, that converts between their rich model and our much simpler model. Notice that nowhere on this map is there a book object. Catalog items, loans, payments, index items. We don't need a book service because book is a noun and our systems should be focused on processes. Each of these bounded contexts has its own specific domain jargon. That's what a bounded context is. It's the set of concepts that you need to understand in order to solve problems. So if you're an archivist, then you need to know about classifications and catalog items. If you're a librarian, maybe you need to do stock takes and do damage reports. And if you're a customer, you need to know when to return an item and whether you're overdue. These things don't overlap at all. They're bounded. Inside each boundary, we use one set of concepts that have rigorous definitions. So that concludes our whistle-stop tour. Let's briefly recap. Our first boundary is the deployment boundary. So we use microservices to separate our systems into pieces that we can deploy individually. We don't share databases or common libraries if we can help it. So when we're looking for deployment boundaries, remember that things that change together ship together, and that every time we reuse code, we introduce coupling between the usages. We talked about temporal boundaries. So we want to do the smallest amount of work we can inside each request, so it can fail individually, and so it runs faster. And then we raise events, so that other systems can be consistent. So in this case, your granny reserves her Maeve Binchy book, and then we notify the search service via EventBridge. The search service can then be updated to say that that book is no longer available for reservation. We talked about conceptual or linguistic boundaries, these bounded contexts. And here we want to divide the system up by knowledge. What's the smallest number of things you need to know about in order to solve a particular problem? So microservices very often align to a single bounded context. Sometimes a service might have multiple contexts. So maybe we have a borrowing microservice and it contains the borrowing context with loans and penalty fees and that kind of thing. But then we've also included the payment context because it makes sense for us to treat these as a single deployment unit and let one team own them and own that whole space. And maybe when the late fees change, we also need to change our payments code. So it makes sense to ship them together, even though they are separate conceptual boundaries. So when we're looking for conceptual boundaries, we're really talking about processes. We're looking for verbs, not nouns. Because if we model around nouns, if we model around the book, we end up with very large, non-cohesive units. And we spent quite a long time talking about consistency boundaries. So aggregates are a way for us to model consistency boundaries inside our domain. Okay, we make the consistency explicit in our code, and that helps us to reason about it, and it helps us to align to the underlying infrastructure. Some bounded contexts will only have a single aggregate, like the payments context, which only has a payment. Others will have several. Okay, so the borrowing context has got a loan, penalty fee, a reservation. These are separate aggregates, but they're inside one context. Maybe they all go inside the same library together because they're part of the same solution space. So when we're looking for consistency boundaries, we use aggregates to make our consistency explicit, and we use eventual consistency between those boundaries. That's everything I have to say. At this point, if we were in a room together, I would ask for questions, but I can't. So instead, if you've got any questions, hit me up on Twitter, find the slides on GitHub, and you should, buy my book.